We want to introduce flux today. Now imagine that we have a surface here that you're going to put, let's say, in a river or a stream. So the surface is porous, maybe like a sheet. And as water is flowing through, it's squirting out potentially in every direction. So if I said how much water is squirting through, let's say at this point, let's call little n the unit normal vector. Then the amount at this point right here would be the amount of F in this direction, or simply F dotted with n. If I then said how much over that entire patch, well, we know that patch is the ds patch. So this would give us basically the amount of fluid per unit of time that is flowing through at that point. So now if we said let's add all of them up over the entire surface, then of course we would be integrating this thing over the surface, and this quantity right here is what we define to be the flux. Now we already know how to find the ds. ds, as we've seen before, the surface area parameter, is fx squared plus fy squared plus 1 under the square root, integrated with respect to a, where z equals f of x, y is currently our surface. So now we want to see how does the n figure into the next calculation. We know the unit vector n points in the same direction as the gradient vector. But right now, our gradient vector must be three-dimensional, and we only have a function of two variables. So we need to create a three-dimensional function in order to take the gradient of it. So I'll create a new function, we'll call it g of x, y, z. Now, g will either be z minus f, or it'll be f minus z. It depends which way the normal vector points. If the normal vector points upwards, then I want the partial with respect to z to be positive 1. If the normal vector points downwards, I would want it to be negative 1. And that will always determine the order of subtraction. Since my vector is pointing upwards, we will write this as z minus f of x, y. Then the gradient of g would simply be negative fx, negative fy, positive 1. The unit normal vector we know is the vector in this direction, so the first thing we'll do is we'll find the length of the gradient vector, which will be fx squared plus fy squared plus 1 under the root. We recognize that quantity because that's the surface area parameter. So now we can express the unit normal vector as 1 over the length of the gradient vector times the gradient vector itself. Now when it comes time to actually calculate this quantity, when we do the f dot n, what we're actually going to do is f dotted with 1 over the length of the gradient vector times the gradient vector. But we do not want to multiply this through because it's going to show up again here. The reason we calculated both times is to make sure we did it right, because we're actually calculating them independently. Now when we do that final process here, we have f dot n ds, but f is going to be a vector with three variables in it, an x, y, and a z in all likelihood. So like we did with the surface integrals, we would need to replace z with f of x, y to make this basically just a two-variable problem. Then this quantity here would become the xy plane here. It will become f dotted with this, and then the surface area parameter So if I did this correctly, these two quantities here should cancel. You don't start by assuming they're going to cancel because, again, you have to find them independently. You actually have to define the function g in order to take its gradient, and you actually have to have this, and signs might actually differ at this point. But this process is very clean and usually presents a fairly simple integration. Now, I've posted several examples on Canvas for the flux, so you can now try this yourself.